Hello, everyone. My name is Halim Acosta, and I'm with the Center for Educational Informatics at North Carolina State University. And today I'll be sharing our work, Multimodal Learning Analytics for Predicting Student Collaboration Satisfaction in Collaborative Game-Based Learning. Satisfaction during students' collaborative endeavors is influential in shaping team dynamics, improving knowledge acquisition, and contributing to overall positive learning experiences. Gauging student satisfaction within collaborative learning contexts can offer insights into student engagement and participation levels. However, much work looking into satisfaction relies on post hoc analysis of survey information, with automated methods of assessment being relatively underexplored. Collaborative game-based learning environments represent a dynamic approach for creating interactive and immersive learning experiences. These environments also afford the possibility of collecting and analyzing student behavior from a diverse array of data sources such as audio, video, and text. While previous work has successfully predicted peer satisfaction in dyadic settings from multimodal data, there remains a gap in exploring the prediction of student collaboration satisfaction in non-dyadic groups. Our study aims to address this gap by focusing on the prediction of student satisfaction during collaborative learning in small group scenarios. We formulate our work to address three key research questions. First, given a range of data channels collected from within a game-based learning environment, we would like to know what are the individual modalities that contribute most significantly to the task of predicting collaboration satisfaction. Our second research question concerns how the integration of multiple modalities using a deep learning model can enhance the performance for the task. Finally, our third research question asks what specific combination of modalities and features are most effective for our proposed model. Additionally, we would like to understand how feature importance analysis can aid in our understanding of the predictive features for our task. EcoJourneys is a collaborative game-based learning environment where small groups of middle school students work together to determine the cause of an unknown illness spreading amongst the fish population on an island. Additionally, EcoJourneys collects extensive gameplay data, including students' interactions, decision-making processes, and learning outcomes. These can be analyzed to gain insights into students' problem-solving strategies and inform instructional design decisions for future iterations of the game. Students must progress through 4 distinct activities within the game, including a tutorial and 3 quests. After each activity, they respond to an in-game exit ticket survey that gathers information about their sentiments regarding their interactions. We collected multimodal data with consent from 55 middle school students as they interacted with the learning environment over a period of 5 to 6 days. After processing and removing students with missing post-survey information, we were left with data from 50 students, resulting in 164 activities containing video and trace log information. Our research utilizes video-based features extracted using the OpenFace 2.0 toolkit from video recordings obtained via front-facing cameras. We utilize the action unit intensity information resulting from 17 distinct facial action units. Head pose information consists of 6 features offering information about head orientation and position relative to the recording camera. Finally, eye gaze information consists of 3 direction-based features for each eye, resulting in a total of 6 gaze-based features. In tandem with facial analysis, students' interactions within the learning environment are captured through trace log data, documenting in-game actions such as NPC interactions, locations visited, evidence collected, and chat messages exchanged. We investigate the efficacy of these multimodal features for predicting student collaboration satisfaction. As stated before, students are given an exit ticket survey at the end of each activity. The survey encompasses 5 questions graded on a Likert scale, aimed at gauging students' perceptions of their collaborative interactions. For our work, we focus on the following statements. 1, I am satisfied with how group members listened, and 2, I am satisfied with how group members are building on each other's ideas. We define collaboration satisfaction through a rule-based categorization of the response to both statements as depicted in the table to the right. Initially, we investigate the predictive performance of each modality employing LSTM models. These baseline models are individually trained utilizing unimodal features to predict student collaboration satisfaction. Through this line of inquiry, we aim to find the best modalities for unimodal models in bolstering student collaboration satisfaction prediction. Our multimodal approach incorporates a deep learning architecture with a cross-attention mechanism. Our architecture draws inspiration from the self-doc implementation of cross-attention. However, we omit the self-attention block immediately following the cross-attention layer. The architecture detailed here employs GRU-based encoders to project data into a fixed dimensional embedding space for each video-based feature. These embeddings are then fed into an initial cross-attention layer, designating one set of features as the key and the other as query and values. It is then added with its inverse representation for downstream processing. Subsequently, these representations are combined utilizing a second cross-attention layer, culminating in a final attention map. We then combine the trace log embeddings and the derived attention map together before it's processed by a feed-forward classification head. Starting with the unimodal results, we found that although AU and pose-only features had a slightly higher accuracy than the trace and gaze features, a Wilcoxon test reveals that there are no significant differences between the overall performance of each modality through cross-validation. Importantly, we see that the full multimodal model significantly outperforms all unimodal counterparts, underscoring the effectiveness of leveraging multiple modalities for predicting student satisfaction. We conducted an ablation study to pinpoint the feature combinations contributing to the improved multimodal performance. As depicted in the table shown, the full model significantly outperforms various ablated versions. While there exists no significant disparity in the performance between the full multimodal model and the trace log plus AU only model, notable differences emerge between these two models and most other feature combinations. Notably, it is important to highlight that several models incorporating gaze feature exhibited a markedly low performance compared to those excluding said features, with the exception of the full multimodal model. To conduct a feature importance analysis, we utilize gradient SHAP to estimate the feature importance for each modality, with the exception omitting trace log data. In these figures, we see that representing AU information for two cross-validation folds, we see that there is variation in specific features that are most informative for the prediction task, while many of the features are uninformative. Despite these variations, AU1 and AU7 appear to be common features that positively contributes across validation folds. These action units are often associated with confusion, boredom, and surprise, which may be important factors in determining satisfaction. For other modalities, we see that the horizontal movement of eye gaze marginally contributed to model performance, although overall gaze features were not shown to be particularly beneficial in predicting student collaboration satisfaction. Head tilt and nodding behavior associated with the z-coordinate of head pose is consistently shown to be an informative feature and enhances the predictive capabilities of multimodal models. There are a few limitations to our work. Notably, we derive satisfaction through a rule-based discretization of student responses to the Likert-valued questions. While this measures an individual's attitudes towards their group interaction, it does not specifically measure how well the group was satisfied with the collaborative efforts. Additionally, we utilize data from a single game-based learning environment with a homogeneous set of users. It is important to note that the proposed method may not generalize well to learners in other populations or learning environments. Finally, during feature alignment, we utilize trace data to discretize the facial feature information. The trace log information has an irregular temporal nature, and by averaging facial feature data in between trace events, we may skew values when there's a large gap in these trace events. To conclude, we contrasted unimodal and multimodal deep learning models to predict student collaboration satisfaction, while they interacted with a game-based learning environment. We explored how various unimodal features contribute to the predictive performance of multimodal models. Additionally, we devised a multimodal model that utilized a cross-attention mechanism to attend to the most salient parts of the data. Overall, the proposed approach showed improved performance over naive and unimodal baselines, and we showed through our ablation study that it can effectively mitigate the inclusion of extraneous and possibly noisy inputs. Our SHAP analysis also revealed a subset of video-based features that consistently contribute to the predictive performance of the multimodal model. That concludes our presentation, and I open the floor to questions.